In this video, we'll look at several examples of differential equations where the auxiliary equation has complex roots. In the first example, we're asked to find a general solution to y double prime plus 2y prime plus 4y equals 0. So first thing we do is we write down the auxiliary equation for this differential equation, which is given by r squared plus 2r plus 4, and that equals 0. Now, we're going to use the quadratic formula to solve this, and the quadratic formula is given by negative b plus or minus the square root of b squared minus 4ac all over 2a. And in our particular example, b is positive 2, a is 1, c is 4. So we get negative 2 plus or minus square root of 2 squared minus 4 times 1 times 4. And we divide that by 2 times 1. Now, we can simplify that a little bit. That's negative 2 plus or minus the square root of negative 12 over 2. I'm going to mark the negative with red here so that it pops. And when we have a square root of a negative number, we can factor out that factor of negative 1. So we can write this as negative 1 times 12. So we get the square root of negative 1 times the square root of 12, and the square root of negative 1 is equal to I. So this simplifies to negative 2 plus or minus I times square root of 12 over 2. And we can then simplify that even further by simplifying the square root of 12. So we get negative 2 plus or minus, and the square root of 12, we can write that as square root of 4 times 3, which is square root of 4 times square root of 3. So that simplifies to 2 square root of 3. So we have plus or minus 2i square root of 3. And then we divide that by 2. And now we see that the 2 can be divided into both of these terms. So the simplified answer here is negative 1 plus or minus I times square root of 3. So now let's compare that with how the general solution, or what the general solution looks like. So the general solution for complex roots is alpha plus or minus beta I. And if you compare that here, we see that alpha equals negative 1, and our beta is square root of 3. Note that the general solution already has a plus or minus. There's a plus or minus here. So we can always pick the beta value to be the positive value. Okay, so once we have that, we're going to look at the general solution. Y of t equals c1 e to the power alpha t cosine beta t plus c2 e to the power alpha t sine of beta t. So I have alpha here, beta here, alpha here, and then beta beta here, and we plug in our two values. And what we get is that y of t equals c1 e to the power negative 1 times t, which is just negative t, and then cosine of square root of 3 times t plus c2 e to the power negative t sine of square root of 3 times t. So we have a negative here, a square root of 3 here, a negative here, and then a square root of 3 here. And that's our final answer. Okay, let's take a look at the next example. We have to find a general solution to y double prime plus 9y equals 0. So let's take a look at the auxiliary equation. And the auxiliary equation is r squared plus 9 equals 0. Now, be careful that this differential equation does not have a y prime, so it does not have a term with r. We only have the r squared and the 9 for the auxiliary equation. And while we could use the quadratic formula here, it would be a little bit overkill because we can use the square root property. So what we can do here is that r squared equals negative 9, and then r by the square root property is plus or minus the square root of negative 9. And now we can pull that negative outside and we get I, so r equals plus or minus I times square root of 9. And then square root of 9 simplifies to 3, so we get that r equals plus or minus 3i. So when we compare that with the general solution, the general complex root, we get alpha plus or minus beta I. Alpha is the real part. There's no real part here, but we can think of that as 0 plus or minus 3i. So that means that alpha equals 0, and beta, just pick the positive value, so we pick beta equals 3. Okay, and now our general solution is y of t equals c1 e to the power alpha t, and our alpha is 0, so I'm going to write in 0 here. E to the power 0t cosine of 3t. And then we have something similar with the sine, so plus c2 e to the power 0 t sine of 3t. Now that can be simplified a little bit because e to the power 0 is just 1. So our final answer becomes y of t equals c1 cosine of 3t plus c2 sine of 3t. And that's our final answer. And in this case, it's not too hard to actually plug that in here and verify that it is a general solution to this differential equation. Okay, the final example for this video is to solve an initial value problem. So we have a problem that basically looks like the two we've done before, but now we have two initial values. So we'll see how we can use that to find our values for C1 and C2. So when we solve the initial value problem, we start out the same way by finding the auxiliary equation, and the auxiliary equation here is given by r squared plus 2r plus 2 equals 0. Now, I will leave it up to you to check for yourself that the solutions here, or the roots, are given by r1, 2 equals -1 plus or minus I. And so that means when we compare it with alpha plus or minus beta, it means that alpha equals -1 and beta equals 1. Again, beta is always just the positive value here, right? So we have plus or minus 1i. Okay, so our general solution is y of t equals c1 e to the power alpha, and in this case that is just a negative t cosine of beta t, so that's just cosine of t, or 1 times t plus c2 e to the power -t sine of 1t, or just t. Now, all that is left to do for us is to find out what C1 and C2 are. And this is kind of the hardest part of this problem, in the sense that it's quite a bit of work. So this is our general solution. And we want to use the initial conditions here. And we see that we're using y of 0 equals 2, and we're also using y prime of 0 equals 1. So because we're using the derivative, we're going to have to find the derivative of this right here. So y prime of t is the derivative of this entire thing, right? So I'm going to write c1 e to the power -t cosine of t plus c2 e to the power -t sine of t. And what I'm going to do now is I'm going to use a product rule here, because we have a product of two functions here twice. So this is equal to, by the product rule, the derivative of c1 e to the power -t times cosine of t plus c1 e to the power negative t, and then times the derivative of cosine of t. So that's the product rule that gives us the derivative of this first term. But we also have to do this for the second part. And the second part looks very similar, right? So we have a derivative of this part times the sine, and then the e to the power negative t times the derivative of the cosine. Oops. And I see that this meant to have this blue. And then we plug in the second part, c2 e to the power negative t times sine of t plus c2 e to the power negative t, and then the derivative of sine of t. Okay, so derivative of c1 times e to the power negative t, that's going to give us negative c1 e to the power negative t times cosine of t. Then derivative of cosine is negative sine, so we get a negative c1 e to the power negative t sine of t. So that's the first line. The second line, derivative of c2 e to the power negative t is negative c2 e to the power negative t times sine of t, and then plus c2 e to the power negative t, derivative of sine is cosine of t. Okay, now that was the hardest work. Now let's look at the initial conditions. So the first initial condition is y of 0 equals 2. So we're going to use this formula here to plug that into. And so when we plug that into our original function, we get 2 equals c1 e to the power negative 0 cosine of t, cosine of 0, right? Because t is 0. And then plus c2 e to the power negative t, and that's again a 0, negative 0 here. So that's a negative 0. And then we have sine of 0. Now, when you plug that in, the nice thing is that sine of 0 That's 0. So the C2 disappears and we're just left with C1 times 1 is 2. So we have 2 equals C1, and we already have C1. Now, the next initial condition is that y prime of 0 equals 1. And that means that we have 1 equals, and now we have to plug it into this guy over here. So that's C1, negative C1, e to the power negative 0, cosine of 0, minus C1 e to the power negative 0, and then sine of 0, minus C2 e to the power negative 0, sine of 0, plus C2 e to the power negative 0, cosine of 0. Right, so we have 1, have a 0 here, a 0 here, 0 here, 0 here, 0, 0, 0, 0. Fortunately, a bunch of this will disappear, right? The two terms that have a sign, that goes to 0. This goes to 0. And so what we're left with is that this is equivalent with one equals, this whole term simplifies to negative C1, and then this whole term simplifies to C2. So now let's plug in that we know that C1 is 2. We add 2 to both sides and we get that 3 equals C2. So our final solution is y of t equals C1, which is 2, e to the power negative t, cosine of t, and then plus C2. C2 is 3. So plus 3 e to the power negative t sine of t. And that's our final answer.